Hello students, and welcome to section 5.1, using fundamental identities. As we start in our introduction here, there is some review material from last chapter to take a look at. To start with the reciprocal identities, you can see that the sine of an angle u, or theta if you recall, could also be used, is equal to 1 over cosecant u. Cosine of u is 1 over secant u, tangent of u 1 over cotangent u. Similarly, the cosecant of u can be written as the reciprocal of sine, so 1 over sine u, while secant 1 over cosine u, and cotangent 1 over tangent u. The quotient identities, the tangent of u is equal to sine of u over cosine of u, while the cotangent, of course, is the reciprocal of that, so cosine of u over sine of u. The Pythagorean identities, probably the most important to start with here, is the sine squared of u plus the cosine squared of u is equal to 1. And then from here you can actually derive the other two. In other words, if you take this equation right here and if you divide it by cosine squared, sine squared over cosine squared is tangent squared, cosine squared divided by a cosine squared is 1, and 1 divided by a cosine squared is secant squared. I would certainly memorize this one as well as the prior reciprocal and quotient identities. However, noting this and this can be derived from that first Pythagorean identity, I wouldn't necessarily argue needs to be memorized. It may help, but then again you can always derive them easily. Similarly to getting this equation, you can divide this original Pythagorean identity by sine squared. So if you take sine squared divided by sine squared, you get 1. Cosine squared divided by sine squared, you get cotangent squared, and 1 divided by sine squared is cosecant squared. All right, the cofunction identities, the sine of 90 minus an angle is equal to its cosine, while the cosine of 90 minus an angle is equal to its sine. Similarly, secant of 90 minus an angle is equal to cosecant, while cosecant of 90 minus an angle is equal to secant. And of course, tangent has the connection to then cotangent, as does, of course, you can see in this equation, just kind of flipped, right? Tangent of 90 minus an angle is cotangent, while cotangent of 90 minus an angle is tangent. The even and odd functions, and I've noted off to the left here of each one what they are specific to even versus odd. The sine of a negative angle is equal to negative sine of an angle, so it's odd by virtue, again, of it being symmetric about the origin. I think of the letter O in odd and then the letter O in origin to help me remember that. A tangent is also odd. Tangent of negative u is equal to negative tangent u. And the same holds true with cotangent as well as cosecant. The only functions that are even are cosine and its reciprocal secant. So in other words, cosine of negative u is equal to positive cosine of u. And again, if you remember the symmetry about the y-axis, if you think about the cosine curve, just like the sine curve, cosine in particular, though, has y-axis symmetry, so it's even, as opposed to the graph of sine having origin symmetry, so odd. So cosine is even, as, like I said, is the reciprocal of cosine, which is the secant. As a tip, for each one of these, there are two other versions that you need to be familiar with. Okay, so that kind of speaks again to the idea of sine of negative equals negative sine, but also it's reciprocal. All right, so, and I've denoted that anyways, I guess. So this tip may be, kind of arbitrary, I guess. Anyways, using the fundamental identities. Example 1. So they start off here by saying if the cosecant of u is equal to negative 5/3 and the cosine of u, the same angle, is greater than 0, find the values of the other 5 trig functions. Now I've already pre-filled in all the notes. I don't always do this, but I did that here so that I can actually get through all the notes for today, or at least make that attempt. When is the cosine positive? In other words, when is the x-coordinate on an xy axis? Because that's what the cosine is, right? The cosine of an angle is the x-coordinate. Well, remember that the first quadrant and the fourth quadrant, go ahead and write those two down. The first and fourth quadrants are where the x-coordinate on the xy axis are positive. When is cosecant of an angle equal to negative 5/3? Where in terms of the analysis, let's take a look. So I'm going to go ahead and have all of you write down that 1 over sine, which of course is the cosecant. That's equal to negative 5/3. But notice what I'm doing here. I'm not just writing 1 over sine as negative 5/3. I'm writing the reciprocal of course, cosecant, which we know to be sine, as of course now, well, the fraction simply is also the reciprocal. So the sine of the angle, the same angle, is equal to the reciprocal of negative 5/3, so negative 3/5. Okay, so we know what the sine is, we know what the cosine is, or at least we know that it's either in quadrant 1 or 4. So we're going to go ahead and assess that because sine is negative in quadrants 3 and in quadrants 4. Remember, the y-coordinate, which is what sine represents, is negative in quadrants 3 and 4 on an xy axis. Well, by virtue of deduction, we can argue that the angle u is technically found in quadrant 4. It can't be in 1 nor 3 because 4 is the quote-unquote overlap of these two cases. Cosine is positive in 4, sine is negative in 4. Together, we know then it has to be in quadrant 4. So I then will draw a picture to accompany what a quadrant 4 angle as such should take shape as. So as you can see, I've got my xy axis, I've got my 4th quadrant terminal side. The angle, which technically is a positive angle in this particular direction, right, with a counterclockwise orientation, with a reference angle really of u here, because we can only draw a right triangle if the two non-right angles are acute. U is the reference angle. Remember, the sine of u is opposite negative 3, there it is, opposite over hypotenuse. So there's your hypotenuse, and there's your opposite, obviously, as we look at it. So opposite negative 3, hypotenuse 5. Yes, your leg can be negative if you draw it on an xy axis. However, the hypotenuse can never be negative. Because the hypotenuse can never be negative, you're going to have answers that in some cases have a positive or negative x, positive or negative y. Now, if you're wondering how I got 4, only having known or being given pardon, negative 3 is the opposite and 5 is the hypotenuse, well, this actually ends up being a 3, 4, 5 right triangle. And you guys are very familiar with 3, 4, 5 right triangles. B, it ends up when you do a squared plus b squared equals c squared. 3, 4, 5. B, of course, must be 4. 3, 4, 5, but it is also a positive, not a negative value. So be careful when you're doing this analysis. It's in the 4th quadrant, but B in this case is a positive x, y is negative. Well, the hypotenuse again is always positive. All right, if we continue, I'm going to go ahead and do all 6 trig functions. Pardon, 5 really that remain. The 6th is given as cosecant. So if we look at the picture, pretty obviously I would argue that the cosine is adjacent 4 over hypotenuse 5. Therefore, the secant is simply the reciprocal of 4/5. We can simply then do the tangent and its reciprocal. So the tangent of u would be opposite negative 3 over adjacent 4, and its reciprocal, of course, cotangent then being negative 4/3. So I do highly recommend you draw a picture when you're doing these problems. You can, and we will later actually utilize one of these Pythagorean identities in context, because that also is an option for solving these. I do like to start, though, with a picture to help kind of formulate or really set up that understanding more fully. Okay, as we move on, we're going to go ahead and take a look now at example 2. It does say simplify, and there's 3 parts here, as you can see. To kick the problem off, it does say, well, for part A, cosecant squared cotangent minus cotangent, and yes, of x in each case. So how do we simplify something of this nature? So speaking of, like I was saying earlier, the Pythagorean identities, but also speaking of maybe, well, gosh, thinking of basic factoring like we did in Algebra 1 and Algebra 2, turns out that the 2 terms, and that's what these are really, these 2 terms, this is a combination of 2 trig functions, but this is obviously still a trig function on its own, of which this is one term and this is another. So these are 2 terms in context. There happens to be, and if it isn't already obvious, there happens to be a GCF. The cotangent appears here in the first term as well as the second term. So please write this down. The cotangent of x happens to be the GCF. So when it comes to using a concept of which you are very familiar with, the GCF, we're going to factor out, as you see, the GCF being cotangent, so therefore after you divide it out, quantity cosecant squared, because that's what's left after dividing out cotangent here. You have cosecant squared. And out of this, of course, cotangent divided by itself, simply just 1. And it is minus 1, of course. Before we proceed, whenever you look at a quantity that you've maybe done some factoring with, but a quantity of which that maybe also still has a squared term in it, there's a good chance that you're still going to have to do some analysis, particularly with, well, a Pythagorean identity. The Pythagorean identity that we are going to reflect upon from up above, which I'll scroll up again, it shows here, as you can see, there's the one we're looking for. 1 plus cotangent squared is equal to cosecant squared of the angle. So in this particular context, I'll go ahead and uncover very much exactly what I just said. There it is. 1 plus cotangent squared equals cosecant squared. Now, it's not exactly what we want quite yet. In other words, if I wanted to have cosecant squared and this constant 1 on both sides, I can subtract 1 from both sides. And look, cotangent squared is technically now equal to cosecant squared minus 1. And that's precisely what we have in this particular quantity. So we're almost there. Now we're going to go ahead and take this quantity. As you can see, I'll uncover it this way. We still have cotangent of x, but now cosecant squared minus 1, look at that. It's cotangent squared of x. And we're one step away, just there, or almost there. And that would be simply multiplying cotangent times cotangent squared. And in effect, it's like saying cotangent of x to the first, the entire quantity, times cotangent of x, the whole quantity squared, which ends up being the following, cotangent cubed of x. Do not mistake that final answer as this. It's not the same thing. Okay, this little cube as opposed to that little cube, this cube is actually indicating the x is being cubed. Well, this cubed is indicating that the whole quantity on its own, cotangent of x, you could even put in parentheses, and then the whole thing is cubed. There is a difference between those two, so please do not write cotangent x cubed. Okay, the notation needs to be written as such. So the cubed actually goes between these two kind of terms, the cotangent itself, but also x. Cubed is in between. All right, as we move on, part B, tangent sine plus cosine. I'm going to uncover right away something that may be obvious or not. If you think about the, the idea of maybe rewriting tangent and then uncovering, as I will here in a moment, what is common between the two. It turns out that there is something to be said about the LCD principle. As a matter of fact, before I uncover that, let me simplify the tangent, which you all should know a little bit about already. The tangent of x, we all remember, hopefully, is the sine of x over the cosine of x. Okay, I certainly recommend you do that with tangent because now the problem has nothing but sine and cosine. It's going to be much easier to simplify. All right, times the sine of x, still plus the cosine of x. Okay, I don't want to uncover too much more because now what I want you to consider is what's common, like the last problem in a sense, what's common between these two. Well, I won't go too much farther in the sense of a GCF concept because it's not really a GCF per se. Because actually, if you think about it, with a common denominator, with this being a fraction, with a common denominator of cosine of x, this is how things are going to unfold. So cosine is multiplied then by this. That's great. Think about that for a second. If now this fraction on its own is going to have a denominator of cosine, well, this fraction on its own is also going to have a denominator of cosine. You now have an LCD very nicely situated to where you can add the two fractions. And I'll uncover everything. So we're almost out of time here, so you guys can see how everything kind of unfolds from here. So the rest of that kind of takes shape as you see. You've got sine squared, because sine times sine is sine squared over cosine. This is cosine times cosine, so cosine squared. Again, you have that common denominator of cosine. In the numerator, you have sine squared plus cosine squared, while the denominator, of course, is combined as one single denominator monomial. Sine squared plus cosine squared, very nicely, of course, is simply 1, while the denominator is simply cosine. And then your final answer, even though I'm uncovering part of part C, it's okay. There you have it. The answer overall ends up being simply the secant of x, which is the reciprocal, of course, of cosine. We will continue this at a later time.